Okay, everybody, time to get towards the end of the unit where things all come together when we use the mold to answer some questions about how we can handle reactions and how we can predict reactants and products in all different ways using the mold. So a couple of enlightening things are going to come along your way with the reactions. And again, we learned the five types of reactions. We also learned how to balance them and put numbers in front and equalize the number of atoms. So let's see how we can use this going forward. Okay, so if we take a look at this little kind of reaction up here, I'll get straight to the point. This is the equation for a tricycle, right? So we have frames, we have three wheels, we have two pedals, which makes a tricycle. Again, if you look at the coefficients here, these are the ratios in the number of parts needed to make a children's tricycle or a child's tricycle, unless you still drive tricycles, then you're not a kid, but you get the idea. So again, these would be the ratio or the relationships of the numbers of particles needed to create a product. Here are your reactants, here's your product. Now, again, with these ratios, we can use this to calculate in different ways. Okay, so for example, so really the coefficients are going to tell in what part ratio needed to create it. So 1 to 3 to 2 for 1 is going to be balanced for the mass of this. So of course the tricycle weighs as much as its parts do. Okay, number 2, we can use this to predict based on the recipe. Again, you could think of this as a recipe for tricycles. We could predict different amounts based on other amounts by using this equation. Okay, and that would be the stoichiometry of the reaction. Which is the relationship of the quantities. Okay, so for instance, if I knew that I had enough frames, okay, I could predict how many tricycles I could make because I know I have a 1-to-1 ratio of frames to tricycles. Right, so if I had 100 frames, theoretically, I know I could produce 100 tricycles. Okay, I could also go back the other way. I could say if I wanted to make 50 tricycles, right, how many wheels, pedals, and frames would I need? So you could predict the products by also predicting reactions in reverse. So there's very powerful ways you can do this. And now with knowing the mole, we can actually do this with elements and compounds as well. Okay, so let's just say you own a bike shop and you get an order for 30 tricycles. So that is our quantity. How many of each part do you need? All right, so if you think about this, if you have a 1 to 3 to 2 ratio, right, for 1, if you know that if you're looking for 30 tricycles, okay, and you multiply this by 30, you know that you would have to multiply this by 30, this by 30, and this by 30, right? Now that's easy to say you need 30 frames because the ratio is 1-to-1, but you would need 3 times that, right, for the wheels. So you would need 90 wheels and you would need 60 pedals. Again, we're multiplying by 30, multiplying by 30, and multiplying by 30. So you can see this becomes the new amounts that you would need, but the ratio is still the 1 to 3 to 2 to 1. Okay? So again, you can do this with any amount of anything and predict. All right, so there's a lot we could do with this. Okay, so again, you can also do it for a 1-to-1 kind of thing. Well, we asked how many of each part, but what if I had 60 wheels? How many tricycles could I make? Well, you can do a simple ratio, right? We know if we had 60 wheels over its coefficient of 3, right? I could make how many tricycles? Okay, over its coefficient of 1, because it's a 3-to-1 ratio. So a 3-to-1 ratio, okay, would be 20 tricycles. Okay. All right, so we get the idea behind this. We can use these ratios to do this. And again, what am I assuming? We're assuming, right, we have to assume that we not have enough pedals, okay, and frames. Again, we always have to do that. We're assuming that we have enough because we're just basing the wheels on the tricycles. All right, so that's important to know. So how do we extend this down to regular chemical reactions? Okay, and again, what's different here is that we can count the particles. Again, these particles are big enough to count, so we're not worrying about weighing or finding volume. If we're doing this in a reaction, we're going to have this complication of mass and volume. So we'll have to deal with that as we move on. All right, so a couple things. How do we actually do this with counting. All right, so I'm going to call this method 1 that we can use the mole ratio. And this is the preferred method I would like you to use. We can use the mole ratio to do this. The mole ratio is the ratios of the balanced equations. Okay, you can also do it by dimensional analysis. I'm going to show you both ways, and you can choose which one you like to use. Okay, really what we're going to do is you're going to be given a gram amount, a liter amount, or a number of particles amount. Okay, so again, grams, liters, and number of particles. Okay, what you're going to do is you're going to want to convert to moles. Okay, so that's going to kind of be step 1. Okay, if you're already in the mole, then you can go right into using something called a mole ratio. That would be step 2. Okay, use that mole ratio. Okay, then you're going to convert back out to your next product or reactant. Okay, and then multiply back out, and then find your grams, liters, and number of particles that you would need for your product or your reactant. Okay, so you're going to relate one quantity to the other by using these steps. Okay, now again, you may not have to do the first step or the third step because you may already be in moles. So we'll have to figure that out. Don't forget, the coefficients are the number of moles. Okay, so I'm going to show you how to use this method. Okay, so let's just say we have a reaction using plants. Okay, so plants produce glucose through photosynthesis, which uses water and carbon dioxide. Okay, and the key now is how many grams of glucose can a plant produce from 200 grams of water? Okay, so we look at the equation, we see that glucose is here, okay, and water is here. So we want to know how much of the glucose we can produce, okay, from your 200 grams of water. So that's what's given to you. And sometimes I like to kind of like jot that in here a little bit. All right, so that's the important point. And we have a 6 to 6 to 1. Okay, here's the 1 ratio between these things. So we're going to assume that we have enough. We're going to ignore the oxygen because that's not the problem. But we're going to assume that from the water that we have enough carbon dioxide, right? We're going to assume there's enough of this, okay? That's called the excess reactant, okay? So we're going to assume there's plenty of that. So really, we want to know from 200 grams of water, how much glucose can we make in a maximum before that glucose runs out, before that water runs out. Okay, so the first step what we want to do is we want to start with what's given. So we're going to start with my 200 grams of water. Okay. Now, in order to figure this out, what I want to do is I want to, step 1, convert to moles. So I'm going to go into the mole. Don't forget, when you go from grams to liters or number of particles, the mole map, we go into the mole, into the mole, into the mole. We're going to divide. So we're always dividing into the mole by the GFM. The GFM of water, we're going to remember, is 18. Okay. And what I'm going to get is I'm going to get about 11.1 moles H2O. Okay. Now, what I'm going to do is I'm going to call this the mole hole or the mole ratio. Okay. And what I'm going to do is I'm going to create a series of fractions, and these are really easy. Now, what you could do is you can manually do this. You can take the 11.1, since it's water, and I'm going to put that above the reaction, 11.1. Okay. I'm going to make myself a fraction. Okay. And I can actually take that now and copy this fraction and make that the first part. So again, putting over 6 moles. Now down here is always the coefficient. The coefficient is always down here on the element or the compound that you're using. And I'm going to set that equal to the substance that I want to find. Okay. So I'm looking for how many grams of glucose. So I'm looking for this. So I'm going to looking for the X amount of moles. Okay, again, this is always in moles. You can only do in this mole area, on this mole, this spot. You can only do it if you're in the mole. I don't know how many moles of glucose. Okay, over a coefficient of 1. Okay. Now again, coefficients always down here. The coefficients, you may want to make a note to yourself. Coefficients are always down this, always on the bottom. Okay, I'm going to close the mole hole and I'm going to calculate cross multiply. So if I cross multiply, I'm going to get 1.85 moles of C26H12O6. So notice I've converted my moles of H2O. I've converted them to moles of this because it's a 6 to 1 ratio. So this must be a 6 to 1 ratio, basically dividing by 6. Okay, and now I have moles of this. But I'm looking for grams. So now that I use the mole ratio, I'm going to convert out of the mole. So I'm going to come out of the mole back to grams by multiplying by the GFM of the substance that I want, which is glucose. Now, glucose, if I add this together, if I add C6H12O6 together, I'm going to find out it's 180 grams per mole. So I did that really quickly. You may have to do that on the side. Okay. So I'm going to multiply by 180 grams per mole, which is the GFM of glucose, and I'm going to get a grand total of 333 grams of glucose. Now, what does that really mean? That simply means that if I took 200 grams of water and I gave it to a plant would take the 200 grams of water, okay, and a certain amount of CO2. And when those 200 grams of water combine with enough CO2, and then the water is disappeared and gone and converts to glucose and oxygen, you would make 333 grams of glucose. Okay, so that's it. And at that point, the reaction would stop, okay, because you would run out of water at this point. You would actually run out of H2O, and H2O would be gone. Okay, and of course, if you run out of a reactant, you'd stop this. Again, just like making tricycles. If I kept making tricycles for frames, wheels, and pedals, and I run out of frames, I have to stop. I wouldn't be able to make it. All right, so that's your answer. So again, what are we doing? Step 1, we're changing to moles. Step 2, we're doing the mole ratio from the balanced equation. Number 3, we're going back out of the mole with the new substance, and we're creating our grams. Now, it doesn't really matter what they give you. They could give you liters, or they could give you a number of particles. You just want to be able to go in and out of the mole. So this happens to be a 3-step problem. You could have 2-step problems. You could have 1-step problem. All the problems are the same. All right. Now, if you want to do this a different way using dimensional analysis, I'm just going to show you. Again, this is not something you have to do. Is using method 2. Okay. So method 2 is the same problem, just using it in dimensional analysis way. Okay, so again, this is the same exact written problem here, okay, in method 2. So it says how many grams of glucose produced from 200 grams of this thing. I have my balanced equation again. Okay, so in this case, I'm going to go 200 grams of water. Okay, and now instead of doing this, I'm going to use my mole ratio. So what I'm going to do is I'm going to take 200 grams of water, and I have to divide by the GFM again, but I'm going to do it a different way. I'm going to take the GFM of water, and I'm going to put it on the bottom because it's grams per 1 mole, right? Remember what the GFM means. The GFM means grams per 1 mole. So I'm going to put grams on the bottom, moles at the top. Now I get rid of grams, okay? Now I'm going to use the mole ratio, and the mole ratio between glucose and water, glucose is the 6, and water is the 1, right? I'm sorry, glucose is the 1, water is the 6, okay? So because I'm in moles of water here, I'm going to open up another fraction, and I'm going to match up the moles of water. So mole of H2O goes here, okay? Mole of glucose goes on top there, right? So I'm going to put there is 6 moles of water for every 1 mole of glucose, okay? Moles of water cancel with moles of water, okay? And now I have moles of glucose. But I don't want moles of glucose. I want grams of glucose. So I'm going to put 1 mole of glucose down here, and that would be my GFM, right? Which is going to be now 180 grams of glucose. Okay. So moles of glucose cancel, moles of glucose sample, and guess what I get? I get 333 grams of glucose. Okay. So either way you want to do this. Okay. Again, here is your mole ratio that we did before, just written in a different way using dimensional analysis. So either way you like this, it's up to you. All right. So I'm going to do one more for you, and then I'll let you go on your way, and you could finish up the next 2 problems. Okay. I'll do one more for you. Okay. And again, this kind of shows you a way you can do it. So if I get rid of that, a little neat way to see it, where you have your different ways to see it along the way here. Okay. All right. So let's just check this out. Let's just say you had, it says how many liters of ammonia can be produced from 155 grams of nitrogen. So again, we want to know, now again, ammonia is a gas. So we want to figure out how many liters. So we're looking for X liters. Again, I don't know how many, but let's just say I have 155 grams of nitrogen. Okay. And that means I have excess hydrogen. So I'm not really worried about the hydrogen. I have enough of that. What's going to run out here is my 155 grams of nitrogen. So if once my 155 grams of nitrogen reacts completely to make ammonia, how many liters would I have left over? Okay, so I'm going to start with I'm going to base that on how much nitrogen I have. So 155 grams of nitrogen, okay, of N2, okay. Again, I can't use grams. I want to be able to use moles, so I can use the balance equation. So I'm going to divide that by 28, which is my gram formula mass, going into the mole. Okay, and I'm going to get 5.54 moles of nitrogen. Okay, so basically this is like 5.54 over the coefficient of 1. So I'm going to put that over 1. Again, I like putting it up in the reaction. It makes me feel good. Okay, and of course, I don't know how many liters over 2. Okay, x moles of NH3 over 2. Notice I'm labeling N2 and H3, labeling my compounds and elements, so I know what I'm dealing with. I'm converting nitrogen to ammonia, so nitrogen is going to ammonia. Okay, and then I'm going to get 11.08 moles of NH3. Right, and then moles I'm happy with, but again, I need liters. How are we going to do that? When we have moles going to liters, we're going to go out of the mole. We're going to multiply by 22.4. 22.4 liters, and we get a grand total of 248 liters of N2. Okay, and that's the idea. If you wanted to see it by dimensional analysis, I'll squeeze this at the bottom here. Okay, so we can do it. We have 155 grams of N2. We're going to multiply that by, again, this is done, but I'm just going to show you, this is the dimensional analysis way. Okay, you would have 28 grams in 1 mole of N2. You would multiply that by the gram. Now you can use the mole ratio. You can say there's 1 mole of N2 for 2 mole of NH3. Good enough? Okay. I would cross out my mole of N2 and my mole of N2. Okay, and now I would say that there's in 2 moles of NH3. Again, I'm looking for liters. So I'm going to go 1 mole is 22.4 liters, okay, of NH3. Okay, and 1 mole of NH3, we cancel out moles of NH3, and I'm left with 248 liters of N2. Notice I'm doing the same thing, dividing into the mole, dividing this by 2, dividing that by 2. Okay, 2 to 1, multiplying by 2 here, multiplying by 2, and then what am I doing? I'm multiplying by 22.4, multiplying by 22.4. Okay, so again, this is your mole hole. Again, the next 2 problems you can do on your own. Okay, I'll check this for you. If I go down and I look at this problem, I can actually give you the answer here. See if you could work this out on your own. Okay, and see what your answer would be. I'm going to get a 2, a 1 when you balance, a 3, and a 4. Make sure you know that. Mole ratio of N2 to H4, N2H4 to 3 would be a 2 to 3 ratio. Okay, really important there. Okay, the answer to B is going to be 5.04 times 10 to the 5th grams of H2O. You don't have to have it in scientific notation, but I did it that way. That's a 5. So 5.04 times 10 to the 5th. Okay, it's going to be a lot. Okay, the balanced equation here would be P4010. Okay, plus 6H2O is going to be equal to 4H3PO4. Okay, that's the balanced equation. Make sure you confirm that you know this is balanced. Okay, so that's a 1, a 6, and a 4 would be your compounds. Okay, and if you did this reaction down here and you did this example for B, okay, so again, the answer is equal to this, and the answer equal here would be 165. Again, if you're close enough, that's good. 165.6 grams, okay, of H3PO4. Okay, so this is your answer here. Again, if you're a little off on these answers, that's okay. If you round slightly, try to use significant figures if you can. And that's it. All right, we'll see you in class.